Okay, so I'm going to show you some examples of these coupled resonators. So obviously I already showed you the coupled bulk acoustic wave filter chip. But I'm going to show you some other implementations. So this one is actually kind of an interesting one. So this one was actually done with comb drive structures. It's kind of a low frequency design. But here we have this explicit diagram where it shows, here's like the mass of the first resonator and the second resonator and the third resonator. And you see, we have the coupling springs. These are the basic, the springs that connect these guys to the chip, and then there are coupling springs that connect the three resonators together, right? So this is exactly what I drew before when I talked about these kind of isolated mass spring dampers, and so each resonator is sort of designed so that it's hopefully more or less identical. And you can see here, if we take the mechanical elements and we draw the equivalent circuit for each one, that each one of these guys is this is the resonator 1, 2, and 3, right? And they look like LCR. They have their motional resistance, inductance, and capacitance. And then here's the coupling springs, right? CS1 to 2, coupling spring from resonator 1 to 2, and coupling spring from resonator 2 to 3. And hopefully you can convince yourself. The idea is that the velocity across this coupling spring is equal to the difference in the velocities, right? So it's like if this is, let's call this x1 dot, and then this is x2 dot, then this thing here is x1 dot minus x2 dot, right? So the velocity across that spring is x1 dot is x2 dot. And so the velocity across that spring is equal to the difference between those two things. And so you can see from just the way the current flows that this is the correct kind of connection to make this equivalent circuit model. And then this looks basically like the ladder filter, right? So it's like it's got a nice resonator structure here, a shunt capacitor that's formed by the spring, and then the next resonator, another shunt capacitor, and then another resonator. Okay, so it's like the one that I already showed you before. And so indeed, this was Clark Nguyen actually built this thing, and here's the thing that sort of shows you why do you care about high Q in this structure. And so you've got, it says resonator tank, coupler, resonator tank, resonator tank. So the resonator tank is what this LC is, the LCR for each of the resonators. And if you look down here, here's what this looks like, LCR, and then the little coupling springs. And each of these resonators has some frequency omega naught, and it says basically, so we need a high Q from each of those individual resonators so that we have low insertion loss. And so this shows at the right a 0.3% bandwidth filter at 70 megahertz simulated, and it says heavy insertion loss for resonator Q less than 5,000. So it's plotted here what the frequency response looks like here in terms of transmission, right? How much signal is transmitted through this filter, and you see that insertion loss is how much attenuation there is in the signal, right? And 20 dB of loss means that only 10% of the signal is passed, right? If you put in 1 volt, you get out 100 millivolts. And so that's what's shown here. If you had a tank, the resonator quality factor is 1,000, then you have only about 10% of the signal gets through. And so you need basically high Q. You'd like to have a Q of at least 5,000 so that you have a very low insertion loss in this filter. So you need to have very high quality factor resonators to make a decent filter. So I'm going to show you a couple of modern implementations of these kind of series resonator structures. So this is from the same paper, coupled Lamé mode resonators. So these ones have, here's the input resonator here, right? So here's the input resonator, here's a resonator at the output, and then there's another resonator in here, and then a couple of other resonators that are coupled to ground. And you notice that they don't need any pickoff electrodes on these intermediate resonators, right? Because they're electrically connected to the same bias voltage, but they don't have any electrodes around them because there's no signals being input to these intermediate resonators. It looks like a checkerboard, And then it has the response where you see basically there's the first resonance, the second resonance, and the third resonance, and there's some noise spikes in here. And so this is showing 110 kilohertz bandwidth. This one is operating at like 173 megahertz. And it says 12 dB of rejection. So that's from the peak to the valley here. This is 12 dB. Not fantastic performance. You'd like to have probably more attenuation than that. This is operating in ambient, so pretty decent performance in air, meaning it's not in a vacuum chamber. Also, you can make coupled piezoelectric resonators, and the way that these guys are made is there are five. Here's the electrical circuit for what this looks like. And so if I sort of sketch on here, here's the input port. This is that first little guy, and then there's a capacitor, a shunt capacitance to ground, and here's the second guy, like that. Okay, and then each of these other 1, 2, 3, 4, 5 is identical. And the trick is that each of these, this guy here is actually made up of 4 resonators in parallel. These are piezoelectric resonators. These are the contour mode type resonators, and they are they're connected in parallel. And the reason why they're connected in parallel to make up each of these guys is because they want this thing to have a low motional resistance. So the idea is basically we have to have low Rx. We're putting 4 resonators in parallel. And this thing ends up having Rx equals to, this ends up, they are able to achieve a motion resistance of 50 ohms in this setup. So this is a measured frequency response. So this is a 5 filter bank, right? So that like it's sort of shown here. They have the green frequency response corresponds to this filter 1 here, and I don't have enough colors to do all these guys. I've got some other colors I can use. I guess I can see that red is this like filter 5, and blue here is filter 4. And then I'm going to say orange here is filter 3. And then there's a color that's sort of a reddish color that I don't have access to here, so I'm just going to make it black. Okay, 1, 2, 3, 4, 5. And so each of these guys has a different pass band. You can kind of see over here, right? So you can see these are the pass bands. Okay, and the idea is that if you wanted to have cell phone, for example, where you're able to communicate with at 5 different frequency bands, right? You could select which filter you're going to use. You could choose filter 1 to pick one particular frequency band, and filter 5 to pick a higher frequency band. So you might select between filters. And this is a pretty small chip. It's like 1.6 by 2 millimeters in size, and it's operating at 500 megahertz or so. So that's kind of a typical piezoelectric series resonator combination. I mentioned that earlier on I showed you the diagram of this coupled 3 resonator filter, and so Clark Nguyen a few years ago actually made one of these things with comb drive. So this is a low frequency resonator, and this is the 3 resonator combination that I showed you the diagram for before, right? So resonator 1, resonator 2, resonator 3. And indeed, I said nobody makes these things with comb drives, but indeed some people have. And so it has differential drive inputs. So it's like this is differential. So we got like a plus VN and a minus VN here, and that's driving basically like plus here and minus here. So this is driven, so it's like pulling it to the top and releasing it from the bottom. And then differential sensing on these sends, right? So you can imagine that that if this is like a positive current, right? So we say this is like plus I, then this guy is going to be minus. Okay. And then it has some amplifiers for collecting the current, and then a differential to single-ended amplifier. So it takes a differential measurement and then it converts it to a single-ended output voltage. And in between, I mentioned on the on that checkerboard filter, there's no electrodes on the resonators in between. This one has some electrodes, but they're only for frequency tuning. So this is the same kind of coupled resonator filter that I showed you before. 3 masses coupled by springs. And this is what it looked like. This is a scanning electron microscope picture, an SEM image of this structure, and so you can see the drive resonator here and the sense resonator, and there's an intermediate resonator in between that has no combs, right? And there are some tuning electrodes on that guy so that they can use the electrostatic spring stiffness to shift the resonant frequency of the center resonator. And here's a coupling beam that's connecting them together. So that's coupling each resonators, and you can see very short folded truss structure. So it's this 32 microns long. This is a 20 micron flexure here, and this shows this is what the frequency response looks like. So indeed, it does look like one of these nice resonator filters, and it has the kind of characteristic 3 peaks that you'd expect. A very nice, a good transmission through this thing, and it says insertion loss less than half a dB, so very good insertion loss. And the only problem is it's operating at 340 kilohertz, right? Which, if you know anything about radio, is basically only used for AM radio, so it's not a particularly useful frequency nowadays, right? If we want to have high bandwidth radio connections where let's say you want to be able to do video conferencing on your iPhone, you're not going to be able to do it at 340 kilohertz because you can't get enough data in a channel at 340 kilohertz. So you need to be operating at high frequencies, a gigahertz or so, where you can have these nice 10 megabit channels, let's say, for example. So interesting technology, maybe not particularly useful. This particular implementation not particularly useful for anything because it's sort of 1,000 times too low frequency. So that's why people don't make these kind of comb drive resonators anymore, and that's why the filters look like the previous ones that I showed you. So either that piezoelectric contour mode resonator or the electrostatic contour mode resonator are the more common kind of configurations to have structures that are operating at a megahertz or more. So I'll talk a little bit about the progress towards those resonators. So a very simple kind of design that people have made is a vertically driven bar resonator. So this thing shown in green here is the resonator beam. It's showing the Q of these kinds of resonators about quality factor is about 10,000. And again, here's this box that has the characteristic frequency 1 over 2 pi times square root k over m, and it turns out this is just about 1. There's a frequency constant here for this first mode. Square root e over rho, e being Young's modulus, rho being density. H is the thickness of the resonator material. So it's the film thickness. And LR is the length of the bridge, right? So that's this dimension here. LR, the length of this bar, and H is over here. H is over here, right? So it's the thickness of the film. And so how this works, again, it's got a polarization voltage on it over there, DC voltage. We have an electrode beneath it. We're applying a little AC signal with that electrode, right? So there's a nice AC input here. And that causes this beam to sort of vibrate at its first fundamental resonance, right? So it sort of looks like a half a sine wave here. And you can, by changing the DC bias, you can use the electrostatic spring to tune the resonant frequency. And so this is showing that, at zero bias, it has about 32.2 megahertz, and by applying up to like 16 volts or so, you get about 1% change in the resonant frequency. So you can tune this guy. If you wanted to make a tunable filter, that would be a useful thing. You could tune the center frequency. And this is the hopefully familiar equation for the electrostatic spring. It's epsilon times the overlap area divided by the gap cubed for the electrostatic spring constant, and it's the BP squared, so the bias voltage squared. And then this is the equation. It's basically the mechanical spring constant. So Km here is the Km is the mechanical spring constant, Mr is the mass of the resonator, and Ke is this electrostatic spring constant here. Okay, and the equation that's shown on the previous slide is for the natural frequency when there's no voltage applied, right? So that's basically this K in the in this equation here is the mechanical spring stiffness. And so this is what one of these structures looks like. It's like you can see there's a 20 micron electrode here, 20 micron wide. It has a 0.1 micron air gap, right? Remember, we want to have a small air gap to have large electromechanical coupling. So this is for to keep eta large. And film thickness 2 microns, so it's made of 2 micron thick polycrystalline silicon here. 2 micron thick. I think it says H is 2 microns, and it's 40 microns, like 41 microns long, right? That's this length of the resonator. And so it's showing a Q equal to 8,000, and it's measured in a vacuum, 70 millitorr. Not very much polarization voltage, so 10 volts on this thing, and it's using 3 millivolts as the AC amplitude, right? So this is the AC input, 3 millivolts. Okay, and you get a nice second order frequency response at 8.5 megahertz. So this is very simple structure, like it's just a bar of silicon. Doesn't get any more simple than that. Fairly high Q. So you could also make cascaded resonators out of this thing, right? So just like we gave the example before, you could take 2 of these bar resonators and couple them with the spring, right? So we have the resonator 1, resonator 2, right? So 1 and 2 here, and a spring in between them. So this is like resonator 1, this is resonator 2, and this is the coupling spring. Okay, and so now we can start to make a resonator that is going to have, it's starting to look more like what we want a filter to look like. You can see DC bias here. This is the input electrode over here. And this is where the output electrode is. So there's basically a sense current, Ix, that's getting dumped into this resistor here. So V out is going to be Ix times this RQ2. Right? So that's how we measure the output voltage. And well, here's what this looks like. Here's an SEM. You see the 2 bar resonators that look each one looks like the individual bars, and then it has this nice coupling spring, very small coupling spring in between them that connects the resonators together. And indeed, you see this, here's this nice response where you get these 2 peaks, and so the roll-off is steeper than it was before, right? Remember, the individual one looks like this. This is the 2 resonators together, and so we have a little bit broader passband. Still, insertion loss less than 2 dB, so that means that we're getting most of the signal through this thing. The rejection is this thing here, right? It's 35 dB. Right? Remember, 40 dB in terms of voltage units is 1%, so that means we've attenuated the signals outside the band by a factor of 100. About, you know, if it was 40 dB, it's like 35 dB here. 15 kilohertz bandwidth at 7.8 megahertz. So this is starting to get to be interesting, right? And so one question you might ask is, why isn't the spring in the middle? And it turns out that if the spring is in the middle, the mass of that coupling spring is comparable to the resonator mass, and it actually ends up being low Q. So you'd actually, rather than putting, the springs don't want to be at, the springs should not be at a large velocity point. They should actually be where there is a large strain. And so you could imagine from Rayleigh-Ritz, the effective mass of the coupling spring is lower if it's at a low velocity point. Remember when we did that integral for the effective mass, it's the displacement, it's actually the square of the displacement that weights the mass of this thing. And so if we put it at a point that has low displacement or low velocity, right? Remember, the displacement mode shapes for these guys look like this, right? Like that. And so instead of putting it at the peak, basically at the antinode, right? And we put it closer to the anchor. And it turns out that the quality factor goes from 24 to 341. Okay. So you might ask, well, what is it that governs the quality factor in these resonators? And one thing that is a problem is energy loss to the anchors. Okay, so so basically the resonator has some mechanical energy in it. We don't want to dump that energy into the substrate. And so the ideal kind of mechanical resonator would be completely free. It would just be oscillating, but we'd have to levitate it somehow. And so instead of doing that, here's an example where you take that same kind of bar resonator, very similar, simple sort of bar resonator structure, right? So this is the bar, okay? And now the idea is that instead of anchoring at its ends, right? The previous example, the bars are basically they're anchored here and here, and then they're free in between. So instead of doing that, what if we let it vibrate, and we put the anchors at really at the nodes of this resonance, okay? And so this is what this picture is showing. The bar flexes like this, and it has, if we think about the side view, of a bar resonance, right? It goes like this, right? And it would, if we drew it at its opposite point in the oscillation cycle, it would look like this. And so it's got these nodes right here, right? So here's the nodes, vibration nodes, right? And the antinode is the peaks, right? The antinodes are the peaks. So at the vibration nodes, the displacement is 0. 0 displacement. So that's the idea of this resonator. We put we figure out where the nodes are for a bar, right, for this resonant mode, and we put the anchors there, and then they have to twist, right, because this thing is as it is bending, you can see here it's like these guys are going to twist. They're called torsional supports, so they're twisting. And so that's what this bar resonator looks like. Again, it has, I'm going to shift back to the smaller view so we can see it a little bit better. So it's got a drive electrode here, and then it has, it is actually, the structure is connected to, it says like it here, ground plane and sense electrode. So the body of the structure is connected to this ground plane, and so we're collecting the sense current through here. This is the sense current, and we're DC biasing here. Okay, and this actually, you notice that the DC bias and the sense current are connected to the same point on this resonator. So this is what's using what's called a bias T. So the way that the bias T works is that we have a, sorry, this is an inductor. It's not a very good inductor. We have an inductor and a capacitor. And then, so basically the AC signal, sometimes people use a bias T for applying an RF input signal. So I'm going to write it like this, VAC, VDC here. And this is going to be VAC plus VDC. Okay, so this is the inductor, this is the capacitor. And so the idea is that at the AC frequency, we pick C and L such that 1 over 2 pi f, right, f being the AC frequency. That's the impedance of the capacitor is going to be much, much less than L times 2 pi f. Right, so the impedance of the inductor is going to be much higher than the impedance of the capacitor. And so the idea is that for the AC voltage, the capacitor looks like a dead short, and the inductor looks like a blocking. It looks like an open circuit. And so that allows the AC to pass through. Right, so AC would pass through. Let me change the color here. AC would pass through this guy like that, and this is the AC path. This is the DC path. Right, so at low frequencies, the capacitor blocks the DC voltage. The inductor lets it pass. Okay, so that's a trick. We can use the same node for both applying a DC bias and measuring a sense current using a bias T. Okay, so you might ask then, what's the benefit of doing this? And it turns out that the that if we so if we compare the clamp beam on the left here, right, that's what this CC beam is, clamp beam. The Q is 840, and it's very similar structure. Now free beam, so it has these torsional anchors over here on the right. Q is 10 times higher, 8,430. So this is basically an example of reduced anchor loss. So this guy has lower anchor loss. So we did a better job of designing the anchors in the structure. These guys are operating at about 50 megahertz. Again, these are more or less the same dimensions. 16 micron beam, about 10 microns wide, 2 micron thick polysilicon, and the air gaps. Actually, the free beam has a bigger air gap. It's 120 nanometer air gap. This is the air gap. Okay, and it's only 30 nanometers for the clamp beam. Very small gap, but they're tested in a vacuum in both of these cases. So the dominant form is the dominant form of loss is the anchor loss. Okay, so wrapping things up, I'll just talk a little bit about gigahertz micromechanical resonators, just to give you some ideas about what people have done here. So I mentioned this before. So you remember Rx is the motional resistance here. So it's square root Km over Q times eta squared. Okay. So to make Rx small, we can either increase Q, like it said here, increase Q, or we can increase the electromechanical coupling coefficient eta. So for a low motional resistance resonator, we want both high Q and high eta. And dCdx, right, which is an eta, is higher for parallel plate capacitors, so we need to shrink the gap. I mentioned that before. So this is an example of resonators made at Intel. They use a 14 nanometer air gap. This is a clamp beam resonator, right? So this is a cross-section view, right? It's going to vibrate like this. Obviously, oops, maybe I'll use a different color because it's hard to see it here. It's going to vibrate like this. Vibration mode. And this is the bottom electrode. And so here's a nice high-resolution SEM. Remember, this is the capacitor, right? This is the MEMS capacitor, the air gap capacitor, and it's 14 nanometer air gap. You can see, like, at lower magnification, you can't even see the gap hardly. And then it's zoomed in here. So how do you make this kind of structure? Well, the way they did this was they deposited a layer of polysilicon. They put a very thin oxide, and they deposited another layer of polysilicon, and at the end they etched away that oxide. So it's they just have a very thin conformal 14 nanometer oxide, and they remove it to make this gap. So this is a way that gets you very high eta. So maximize with the small air gap. Okay. So to increase the resonant frequency, to make a high-frequency resonator, one way to do it is to, well, we know omega is square root K over M. So one way to make a high-frequency resonator is to make the mass go to 0. And this is from Mike Ruckus's group at Caltech. So he does a lot of work on nanomechanical resonators. This is a very small, it's a nanowire resonator. And these guys are coupled. It's basically like a bar resonator here. Actually, this is not the best color. It's this bar structure and another bar over here. And there's a coupling spring in between them. So certainly you can make nanowire resonators. They have very little mass and they can operate at very high frequencies. Mike Rukas is a physicist, and so he's interested in doing these kind of fundamental explorations here. It says a sensitive probe of phonon transitions near absolute zero temperature. I'm not going to write that down. Okay, so another way to make the mass equal to zero without making a nanowire, you could make, so for example, this shows a comparison again from Intel. So this is a large bridge resonator. This is just like that clamp beam resonator I talked about before. So if you have one that's 35 microns long by 16 microns, that's large. It's maybe not large by most people's definition, but for Intel it's pretty big. So this thing operates at 3 megahertz. So you can shrink it down. So if you make it half a micron beam, half micron by half micron, now suddenly you're operating at 1,000 times higher frequency, 2 gigahertz. So make the mass go to zero, make the size of the resonator scale down, right? So if you think about it, if we scale down the characteristic length of something by, let's say, a factor of 10, then we get a factor of 100 reduction in mass. Okay, and so this guy is scaled down by, let's see, factor of 100 on the sides. Okay, so it's a big reduction in the mass. So another way to increase the resonant frequency, instead of making the mass go down, right, it's a very simple equation, right, so omega square root k over m, the other way to do it is to, instead of making the mass go to zero, make the spring rate go to infinity. So basically make it very stiff. And so this is a picture from Clark Nguyen's group of a sort of a circular resonator structure. It's a disk resonator. So it has the actual resonator body is this disk, right? This is the resonator, and it has these nice circular input and output electrodes, right? And there's an air gap in between them, and it's anchored in the middle. So this thing kind of looks like a mushroom. So if I drew a cross-sectional picture of it, it would look like this. I remember maybe a picture of this later on. So it's sort of anchored in the middle, and then it's basically going to oscillate in a in kind of a breathing mode. So it's going to basically be oscillating like this, right? So if we imagine it kind of going like that, it's expanding. They call it a breathing mode because it's basically the expansion of this resonator. And again, it's they're actually using both of these electrodes on the sides as inputs. So they basically have an input here and an input here, same signal, and then this is the output electrode and the DC bias. So this has to be measured with a bias T, same way. So it has one output electrode for basically bias and output. You have to use a bias T. It's got a 17 micron radius. And so this is, again, it's operating at 156 megahertz, so interesting frequencies. Q is 9,000, so very useful. Only 35 volt polarization voltage, 2 micron thick layer, and it's got a very narrow gap is one thing about this thing. Very small air gap, and I'll talk about how that's made in just a second. So take this resonator operating at 156 megahertz, okay? If we want to go to higher frequencies, if we want to go to gigahertz, right, we could do the Intel example. We could make the mass go to zero, right, and so we could make this thing really teeny tiny, like a 1 micron disk or something, or maybe a 0.1 micron disk. Not very easy to do that without an electron beam lithography system, but the other way to do this is to go to higher spring stiffness, and so the answer to that is to use a use a stiffer material. And indeed, actually, what Clark Nguyen's group has actually done now is they started to use diamond for these structures. This particular one is made out of polysilicon, and it shows here, okay, so 1 gigahertz, 20 micron disk diameter, measured in vacuum and in air, right? So this is vacuum, this is in air, and look, the Q is almost the same. Okay, so at 1 gigahertz, doesn't matter if you're in vacuum. So it says here basically little energy loss to the ambient. It's most of the energy loss through the anchor. Okay, so it's anchor loss. And this is what the resonance peak looks like. It has 12.9 volt polarization voltage. And I didn't really talk about electromechanical amplitude modulation, but that's, for those of you who know what that is, they actually have to use EAM. You can see the measured data doesn't really match exactly the expected value away from resonance because there's a bunch of feed-through in this thing. So if you understand what that means, then good. If you don't, I'm sorry. So how do you make one of these things? That's the last thing I'll mention to you. Okay, so how does this work? So the way they did this was they start with, again, a silicon wafer. They have some insulating layers here. They have a, in this case, actually, this structure is made out of, let's think about this. So this is made out of plated gold. And, yes, okay, now I remember. So actually what this is, it's a polysilicon resonator, and they're going to electroplate the electrodes. So this, whoopsie, this structure that's shown here is, I'm going to try to shade it in. So this part here is polysilicon. That's probably a bad color because I'm going to use gold for the metal. So this is the polysilicon part inside here. And then what they do is they electroplate these metal electrodes around this thing. Okay, so how did they do this? They started with polysilicon is the green material here. So this is, excuse me, this is the polysilicon. They deposit a very thin layer of oxide. And it's probably actually by thermal oxidation. So they grow a thin thermal oxide. So this could be like 100 nanometers. Okay. Then they're going to deposit, in step B here, they're depositing a seed layer. This is a metal layer used for electroplating. They put photoresist down, and they etch it back. And so now what's happened is it has they've created this this area where they've exposed some of the seed layer, and then they strip it off. So they strip off the seed layer from these regions. They don't want to plate anything on top. Then in the next step, they create a photoresist mold, okay, and they plate gold, okay, and so now these are the gold electrodes, okay, and then remove the oxide, and now they have this plated, they plate nickel on top of that, and I think it's electroless nickel, so it goes down only where there's metal. And the last step, they remove the oxide. So they etch the oxide. And so now, actually not shown in here, if I zoomed way in, so I'm going to sketch this by hand. So the idea is that if we think about our resonator, it was poly, and then it has like some oxide on top of it. Here, I better do it like a bigger picture than this. This is the polysilicon resonator. Here's my thin oxide. So 100 nanometer SiO2. And then we have our nice plated electrodes. Like this. So this is gold. Okay, and we then etch away that oxide. So after oxide etch. Then what we're left with is a disc with metal electrodes and an air gap. So we have in here 100 nanometer air gap. So that's how you make a submicron gap resonator without having to have submicron lithography or a focused ion beam tool. And that is all that I have for this lecture, so thank you very much, and good luck with your summer. Bye.